This is a quick review of Pythagorean triples, which are whole number values that can be sides of a right triangle. Now remember, if sides are whole numbers and a squared plus b squared is equal to c squared, then you have a Pythagorean triple with a, b, and c whole numbers. So in other words, they're not going to be a radical expression that can't be simplified. So some examples: 3, 4, and 5 represent sides that could be sides of a right triangle because 3 squared plus 4 squared is equal to 5 squared. 9 plus 16 is equal to 25. So that's a Pythagorean triple. That one's easy enough to check because the arithmetic is fairly easy. However, there are some Pythagorean triples that you should know that have numbers that are slightly larger. So 5, 12, 13 is an example, because 5 squared plus 12 squared is equal to 13 squared, or 25 plus 144 is equal to 169. There are several other Pythagorean triples that you should be memorizing, and let's make a list of all of the ones that you need to memorize. 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41, and 11, 60, 61. What you're going to notice about the pattern for each of these is that the shortest side is always an odd number, and the two longer sides only differ by 1 unit. And quick check, what happens if I add the two longer sides together? We get 60 plus 61, which is 121, which happens to be 11 squared. The same thing is true for each of the other Pythagorean triples. 40 and 41 added together are 81, which is 9 squared. 24 and 25 added together are 49, which is 7 squared. 12 plus 13 is 25, that's 5 squared, and 4 plus 5 is 9, which is 3 squared. That makes it a little bit easier to memorize all those Pythagorean triples so that you don't have to square 60 and 61 or 40 and 41, all those large numbers. These are intended to be from memory. So for example, if you see a right triangle with whole number lengths in the two given sides, 9 and 41, and we're looking for that third side, you might suspect, because the numbers are large, that it's a Pythagorean triple. We need to remember our Pythagorean triple, which is 9, 40, 41. Quick check, 40 and 41 are 1 unit apart, and they add up to 81, which is 9 squared. So x must be 40, 41 being the hypotenuse, or the largest side. Here's another example. We've got a right triangle here with a hypotenuse of 61 and a longer leg equal to 60. And so we're trying to find that shorter leg. And we could do this: x squared plus 60 squared is equal to 61 squared. However, the arithmetic might be a little bit difficult there, so we want to be able to memorize the Pythagorean triple. And our Pythagorean triple, if you remember, if the two longer sides are 1 apart, then they add up to 121, which is 11 squared. So 11 must be the shortest side. So x must be 11. This is going to make it much easier than doing all the work for the Pythagorean theorem. Now beware of a question like this, because this is a right triangle and we can use Pythagorean theorem. However, it might be tempting to say, hey, I remember that 3, 4, 5 is a Pythagorean triple because 4 and 5 are 1 apart and they add up to 9, which is 3 squared. However, 5 has got to be the longest side, and it's not possible for x here to be the longest side since that's not the hypotenuse of the triangle. So in this case, we are going to have to do the Pythagorean theorem. X squared plus 3 squared is equal to 4 squared. And that would give us x squared plus 9 is equal to 16. Subtracting 9, x squared must be 7, and x will be equal to the square root of 7. So we have to use Pythagorean theorem in that case. So beware of that. Remember that we've got to have the longest side be the hypotenuse. Now here's a fun example that takes this a step further. We have a right triangle, and the two longer sides are 48 and 50, which in this case are not one apart. They're actually two apart. But what you might notice is that because they're two apart, they are both divisible by 2. So 50 is 2 times 25, 48 is 2 times 24. So what we see is that we have a triangle that could be similar to a smaller triangle where we have the side lengths that are half as big, 25, 24, and now we have two longer sides that are 1 unit apart. 24 plus 25 is 49. That gives us a 7 as the missing side. And so our triangle that we were looking for x in is twice as big in terms of the side lengths as the similar triangle. So x must be 7 times 2, which is equal to 14.